All right, so now we're going to start 5.1 part 2. And this is where we start identifying significant results with the range rule of thumb. So the range rule of thumb for identifying significant values is, here's our mu, which is our mean. And we have to know our standard deviation. And if I say mu plus 2 times our standard deviation, whatever that number is, if it's that number or above, it's significantly high. And if it's mu minus 2 times the standard deviation, then if it's that number or below, it's significantly low. And anything else between those two values are not significant. What I mean by not significant is that they're not out of the ordinary, okay? So let's see what we have here. So identifying significant results. We found that when tossing 2 coins, the mean number of heads is 1. And the standard deviation is 0.7. Actually, we found the same thing, right? And we want to use those results and the range rule of thumb to determine whether 2 heads is a significantly high number of heads. So I'm not going to draw as pretty a picture, but I can draw, here's my mu, which equals 1. Then I have mu plus 1 standard deviation is equal to 1.7. And mu plus 2 standard deviations is 1 plus 2 times 0.7. The 2 times 0.7 is 1.4. So this is equal to 2.4. And anything above here, 2.4 or above, would be considered significantly high. Okay, I mean, if you flip 2 coins and you get more than 2 heads, that would be pretty amazing. I would definitely say it was significantly high, right? And I'll do it in red. I can also go this way and I can say mu minus 1 standard deviation is 1 minus 0.7. So that's 0.3. And mu minus 2 standard deviations is equal to 1 minus 2 times 0.7. 2 times 0.7 is 1.4. 1 minus 1.4 is a negative value, negative 0.4. I don't think you could actually get that value. Actually, I'm sorry, it's 0.6. Negative 0. No, it's negative 0.4. Yes, 1.4, 1 minus 1.4 is negative 0.4. So anything, if I got a negative probability, which I don't think I can get, I would have, this is, I'll just write significantly low, like that, okay? So use the results and the range rule of thumb to determine whether 2 heads is significantly high. Is a significantly high number of heads. Well, where is 2? Let's do it with this. So 2, if this is 1.7, this is 2.4, let's say 2 is right here, okay, somewhere over here. Well, it's not significantly high and it's not significantly low. It's just right in the range of no significance. So no, it's not either significantly high or significantly low. Oh. How did that get there? Did it? Oh, okay. I don't know what that was, but it seems to be gone now. Example, identifying significant results within the range rule of thumb. Based on these results, we concluded, we conclude that 2 heads is not a significantly high number of heads because 2 is not greater than or equal to 2.4, which is exactly what we said. So no, we're good. So identify significant results with probabilities. Significantly high number of successes, X successes among N trials is a significantly high number of successes if the probability of X or more successes is 0.05 less. So why do we need that? Because we also have these continuous functions that we really can't count. So we're going to learn how to do this, but we do need to know that. Okay, hold on a second. Okay, there we go. So this is our magic number. If the probability of whatever we're looking for or more is less than or equal to 0.05, it's significantly high. So basically, that would be more like that graph where we talked about the height. And let's say this is the mean. And we have our bell curve. If the probability, which is the area under the curve, let's say that probability that I just colored in is 0.05. Okay, so this is our X, and we're saying the probability of X or more. If it's in this yellow, then it's 0.05, or it could be less if it's further over. And the same thing is true over on significantly low. So let's say this is our point of X. This would be X plus 2 times the standard deviation, if I could find it. And this is X minus 2 times the standard deviation. So anything lower would be the area under the curve to the left of that line. And that would have to also be P of X, X or fewer, is the probability is less than 0.05. Okay, or that area is that small. And this is kind of important. The value 0.05 is not absolutely rigid. Sometimes we could use 0.01 because maybe we want them to be even more significant, right? So it's not rigid, but that's the number we're mostly going to use. All right, so now we're going to talk about the rare event rule for inferential statistics. And let's read what it says. So if under a given assumption, so we're going to make an assumption about some event that's going to happen, the probability of a particular outcome is very small. So when we do our experiment, the probability of each outcome is very small, and it's so small that it occurs significantly less than or significantly more than, so in the upper 5% or the lower 5%, than what we expected it to be. Then basically what we are saying is that our assumption is probably not correct. Okay, so that's really what this says. Okay, and now we have something called the expected value. The expected value of a discrete random variable is equal to the mean. So expected value, mean, same thing. We can therefore find the expected value by multiplying our X times our probability that our X occurred all for each event, for each thing, and then we add them together, which is basically what we did when we found mu. So let's do an example here. I'm going to put in a new slide. All right, so I put in an extra page. Let's see if we can just copy this and this. Okay. So A is what we're going to do first. And it might be easy if you want to draw like a table. It's up to you. So when we draw a table, we could say that the probability of losing, losing, winning, and here's my X, and here's my P of X, and my expected value is the same as the mean. So what we're going to do is put another column here, which is X times P of X. All right. So first one, if you bet $5 on the no, actually, let me move this lose down a little, sorry. Okay, so if you bet $5 on the number 7 in roulette, the probability of losing $5 is 37 out of 38. So if we lose, our probability is 37 out of 38, and we would lose $5, right? And if we multiply those two numbers together, we get, hold on one second. We get negative 4.868. That's close. That's good. Well, I'll put a 4 on the end here. Okay. Now, if we win, let's see what happens. So we bet $5, and the probability of making a net gain of $175 is 1 out of 38. So we could get 175 times 1 out of 38. And that's 4.6052. Okay. And so let's add those up, because remember, it's the sum of that. So I have that minus that, 684. So my net, or I'm sorry, my expected value is going to be equal to negative 0.26. So I expect that if I play this game long enough, I'll lose 26 cents on every time I play, right? And maybe I'll get really lucky and I'll win. But in general, that's my odds, or my expected value, not my odds. Okay, so that takes care of this one. Now, oh, no, sorry. Oh, I guess we can look and see. So did we get it right? It looks like we got it, okay? Now let's do craps. So I need to put, insert a new slide. And let's go back and get this and this. All right. So here's B. We'll do the same thing, make a little table. So I have lose, win. I have my X. I have my P of X. And I have my X times P of X, right? Okay, so if I bet $5 on the pass line in the dice game of craps, the probability of losing $5, so I'm going to lose $5, is 251 over 495. And that number is, I bet you're wondering why I didn't get these numbers before I started. I don't know. Okay, so this is negative 2 point, yeah, good. Negative 2.53535. I don't think I need that many numbers, but let's see. Now, the probability of making a net gain. So if I win, then I will win 5. And the odds of that are 244 over 495. So that becomes 5 times 244 divided by 495. And I get 2.4646 and so on. This kind of just keeps repeating. So now let's see what our net is, right? Or my expected value. So to find my expected value, I sum these. And I'll get my expected value. So I have 2.4, but I have that number minus 2.53535 equals, and that is negative 0.07. Okay, so that is my expected value if I play craps. And let's see, I bet $5 in the pass line. I don't really know craps, so I'm just going to have to read it. Probably losing $5 is this. So if we bet $5 on the pass line and win, we get our $5 back and we get an extra 5, which gives me $10. If we lose, obviously we lose all our money. So now the last thing it says is, which of the preceding two bets is better in the sense of producing higher expected value? So I have, oops, that wasn't mine. Well, we can use theirs. So we have an expected value here of negative 0.26. I got both of them here. So negative 0.26, and we have negative 0.07. And we want to know which is bigger, because the bigger the expected value when I gamble, the better chance I have of winning. And and if you look on a number line, here's 0, and here's negative 1, negative 0.5. So negative 0.26 is somewhere around here, and negative 0.07 is somewhere around here, right? So the more to the right it is, the bigger the number. So what I want to do is play craps, because I have a better chance of actually winning. Okay. And the last slide here is the interpretation, which hopefully says exactly what we just said. So the $5 bet in roulette results in an expected value of negative 26 cents, and the $5 bet in craps results in an expected value of negative 7 cents. Because you are better off losing 7 cents than losing 26 cents, the craps game is better in the long run, even though the roulette game provides an opportunity for a larger payoff when playing the game once. So basically, if I play roulette, I could win $175. But if you can see this, the odds are very small that I will. So I would have a better chance playing more games of craps and producing a better win in the end. And that is basically the end of 5.1. Oh, I have problems to do. Never mind. Hold on. All right, so let's go through a couple of problems that I picked that should help us understand how to do some of the homework problems. So the accompanying table, which is right here, describes results from a group of 10 births from 10 different set of parents. The random variable X, here, let's look at it first while we're reading. So here's our table. The random variable X represents the number of girls among 10 children. Use the range rule of thumb to determine whether one girl in 10 births is a significantly low number of girls. Okay, let's do it. So first we're going to go into StatCrunch. And there's our probabilities. And what I'm going to do is put these side by side. All right, so what's the first thing I want to do? Honestly, the first thing I want to do is look at my values. They're all between 0 and 1, so that looks good. I want to go into my summary stats columns, and I want to sum up my probabilities and make sure that it equals 1, and it does. So now I know I'm in good shape as far as that's concerned, right? And now I'm going to go Stat, Calculator, Custom, because this gives me, this allows me to work with my X values and my probabilities. And now I compute this. So I have found that my mean, we can't really get the actual number in StatCrunch that I know of. So I can get the mean, which is 5.035. And I can get my standard deviation, which is 1.703. That's sufficient. Okay, now the range rule of thumb, if you remember, we had a line and there's some, right here is the mean, okay? And let's say this is one standard deviation. Oh, let me write it better. Sorry. So this is one standard deviation away from mu. So this would be mu plus one standard deviation. And let's say this is mu plus 2 standard deviations. So the maximum value, so use the range rule of thumb to identify a range of values that are not significant. So we want to find the largest value before I go into my significantly high values, right? And my significantly high values are going to occur from here on, right? And well, let's do that first. So I have mu, which is this number right here, is equal to 5.035 plus 2 times 1.703. And I'm going to get out my handy dandy calculator. And I have 5.035 plus 2 times 1.7. And I get, and we're only getting around to one decimal place anywhere, so I really went overboard. So 8.4. That's the value I get. And let's plug it in and see if it works. 8.4. Check. All right, perfect. So now what we want to do is, here, let's see if I can move this or if I lost it. No, it doesn't look like I can. Okay, let's see if I can erase it. Oh, good. Okay, I can erase it. All right, so now we want the minimum value. So now we have to go the other way, right? So we go here. This is mu plus 1 standard deviation. And let's say this is mu plus 2 standard deviation. I'm sorry, minus. Minus, because we're going to the low side, right? So I don't care about mu plus sigma, but I do care about mu, which is 5.03554. No, it's just 35, sorry. Minus, so before we added that 2 times sigma, now we're going to subtract it. And that gives me that is not a smiley face. I'll fix it. It's an equal sign. So 5.035 minus 2 times 1.7 is rounding to 1 decimal place. So this is an equal sign. 1.6. Okay. So let's type in our 1.6. Check it. Perfect. Okay. So that handles that. Now I'm going to erase the screen. And let's see if we can answer the questions. Based on the results, is 1 girl in 10 births a significantly low number of girls? Yes, it is, because if I draw my picture, let's take a new color. All right. So let's say I draw my picture, right? And we know that here is our mu minus 2 sigma, and that value is 1.6. So anything below that value, anything lower than 1.6 is significantly low, right? So is this a significant? Yes, it is. 1 girl is a significantly low number of girls because 1 girl is above the range of values that are not significant. Nope. Because that would mean it's here in this middle part. Here, let me draw the whole thing. I think that would help. So right here, this is 8.4, and this is mu plus 2 sigma, and anything out here is significantly high. So what is that telling me? It's telling me that between here and here is not significantly anything. It's just normal, okay? So what I would do is say, so let's look at yes on B. One girl is a significantly low number of girls because one girl is above the range of values that are not significant. So that would mean they're in the yellow, but that's not helpful. Yes, one girl for C, yes, one girl is a significantly low number of girls because one girl is below the range of values that are not significant. That's my answer. It's below, it's lower than, this is, here, first let me check. Good. And I'm going to write in, let me go back to that question. We're not doing it again. I just want to write this in. So here, these are significantly low, significantly high. And here, between those two, these are not significant. Okay, so that last one was in the not significant. It goes away because I don't have it set up as homework. So when I go back, it gives me a new problem. All right, let's go to number 2. The accompanying table describes a random variable x, the number of adults in groups of 5 who reported sleepwalking. And we have a lot of parts A through D. So let's open this in StatCrunch. Oh, let's see if it opens over the top of that. No. So I have to still put that over here. Close this. And again, my x's are numeric. My probabilities are between 0 and 1. And just to make sure everything is fine, I will sum my probabilities and I get 1, so all good. Find the probability of getting exactly 4 sleepwalkers among 5 adults. So I'm going to go to Stat, Calculators, Custom. We've done this before, but this is a little different. And I hit Compute. So now here, I get my probability distribution, right? I get my mean, I get my standard deviation, but I also have this other part down here, which actually tells me something. So this says the probability of X, and what I want is X equals exactly 4, right? I hit compute, and my answer is right there, 0.023. Perfect. Find the probability of getting 4 or more sleepwalkers among 5 adults. So I want 4 and 5. So I want greater than or equal. And I actually have to retype 4 or else it won't recalculate. And hit compute. And now I have 0.03. Check answer. Perfect. Which probability is relevant for determining whether 4 is a significantly high number of sleepwalkers among 5 adults? The results from part A or the results from part B? So remember, if we have our little line here, and this is our mu, and right here is mu plus 2 sigma, right? This, we want to know what that value is. That value is going to give me whether or not something is significantly high or significant or not, right? Also, we have the probability that we know that the probability that X, or the number of sleepwalkers, is greater than or equal to 4 is 0.03. Is 0.03 greater than? So 0.03. And remember, our this piece here is 0.05 on this end, and the smaller one would be 0.05 on that end. Okay, so yes, 0.05 is smaller. I'm sorry, 0.03 is smaller than 0.05, which means that both 4 and 5 adults are a significantly high number of sleepwalkers. So since the probability of getting fewer than 4 sleepwalkers is the complement of the results, this is the relevant probability. No, it has nothing to do with the complement. Since the probability of getting 4 sleepwalkers is the result from part A, this is the relevant probability. Well, that's true, but I really want to know where my stop point is. And if I look at greater than or equal to 4, I'm still getting less than 0.05. So now I know 4 and 5 are significantly high. Since the probability of getting 5 sleepwalkers is less likely than getting 4 sleepwalkers, that's true. The result from part A is the relevant probability. No, because if I add a little bit more, I still am smaller than 0.05. So let's look at the last one. Since the probability of getting 4 or more sleepwalkers is the probability of the given, which is 4, or a more extreme result, which in this case would be 5, the result from part B is the relevant probability. And that really is what we are going to use. Take our check. Perfect. Okay. Is 4 a significantly high number of 4 sleepwalkers among 5 adults? Yes. Because when we look, it's 0.023, which is less than 0.05. So yes is the answer. So it's one of the first two. Since the appropriate probability is greater than 0.05, no. Since the appropriate probability is less than 0.05, yes, it is a significantly high number. Exactly. Check answer. And there we have it. Okay. Erase what I have here. And let's look and see what problem 3 has in store. Okay, so problem 3, we're going to do something similar to what we did as the last problem here, right? And I don't think I need stat crunch for this. All right. Okay. So when playing roulette at a casino, a gambler is trying to decide whether to bet $15 on the number 36 or $15 on the outcome of one of these 5 numbers. So the gambler, well, let's just look at A. Find the expected value for the $15 bet that the outcome is 000123. Okay, so let's do that first. We're going to start with our table. And my expected value is going to be, so we have lose, win, we have our x, we have our p of x, and we're going to have our x times p of x. Okay. So if I lose, that means I lose $15. And what's the probability that I'm going to lose $15? Well, it's going to be, I have 5 out of 38. So it's not going to be one of those 5. It's going to be 33 out of 38, right? Because if it was any of the 5 numbers, then I would win. So let's see what that number becomes. I don't know how to, I don't see a way to do this in StatCrunch. You do have to actually calculate this out. So we have 15 times 38 divided, 15 times 33 divided by 38. So this is negative $13.03. Okay. If I win, so let's see. If I win $90. So I have 90 times 5 divided by 38. And that equals positive 11.84. So my expected value here is going to be that number. I just sum these. So my expected value should be negative $1.19, rounded to the nearest cent, is my expected value. Okay, let's see if we got it. Negative 1.19. Check. All right, very good. Since the expected value of the bet on the number 36, so that's 79 cents, negative 79 cents, which is bigger, sorry. So negative 79 cents is greater than negative 1.19. It's better to bet on the single number. Check answer. There we go. And last. All right. There is a 0.9988 probability that the randomly selected 30-year-old male lives through the year. Okay, well, that's important information. Okay. A life insurance company charges $162 for ensuring that the male will live through the year. If the male does not survive, the policy pays out $100,000 as a death benefit. So, from the perspective of the 30-year-old male, what are the monetary values corresponding to the two events of surviving the year and not surviving the year? So the value corresponding to surviving the year. So if I make it through the year, guess what? As the guy who took out the policy, I lost $162, right? However, if I don't survive, I don't make any money, but whoever I leave that to is going to have a profit of $100,000. $100,000 minus the $162 that I initially put in. And let's see if that's perfect. Okay, so this number right here, just so I can put on the screen, is $100,000. That's what that's the payout minus the $162 that was paid for the policy. If the 30-year-old male purchases the policy, what is his expected value? Okay, so now for this, we need to make our table, right? So let's say he survives. If he survives, my X is negative 162. And the probability of that happening is point. So it's right here. Let me highlight it. Okay, so that's the probability that he's going to live through the year. So we have times 0.9988. And then I need another column here, don't I? X, P of X. So I'm going to multiply 162 times 0.9988. That is negative $161.81. Does not survive, not survive. Now we have our X is, so if I don't survive the year, then I have 99,838. My probability is 1 minus this. So it's 0.0012. And that value gives me 99838 times 0.0012. That's positive $119.81. So my expected value is the sum, right? So let me subtract 161.81 from that, and I get negative $42. Okay, so that looks like my expected value. Let's see if I'm right. Negative $42. All right, perfect. Let me erase that. Okay. Can the insurance company expect to make a profit from many such policies? Well, sure. Because the expected value to the 30-year-old male is negative $42. That means that to the insurance company, for every policy they sell, they make an average of $42, don't they? So yes, because the insurance company expects to make an average profit of $42 on every 30-year-old male it insures for 1 year. And there we have it. So I hope that's enough information for you. If you have any questions, of course, don't hesitate to ask. Thank you for watching, and I'm sure we'll do this again real soon. Have a good one. Bye.